Okay, welcome to Lecture 9. In this brief lecture, we're going to take another look at pointers and C-strings. We're also going to introduce the idea of constants. We'll see that assignment has a value and that you can stack up assignments from right to left. And in the second half, we'll take a look at something called the switch decision, which is an alternative to the if-else decision sequence. It's cleaner for certain specific types of decisions, but not as flexible as the if-else. The first few slides are a review of the tail end of Lecture 8, and I just want to throw slide 6 up here as a reminder. This is a vitally important thing that you should use to quiz yourself. Whenever you see a variable declaration in some code, you should be able to describe all of these characteristics of that variable based on the declaration. And if you can't, if you use this as a checklist and you discover that you can't identify some of these things, there's a gap in your knowledge that you should fill in. Okay, so onward ho. Here we're taking another look at the display stir function that we introduced in the previous lecture. There's a subtlety to this function that I didn't get into when we first talked about it, which is that a string literal, such as hello in double quotes here, is stored in memory, specifically in the static data area, as a null-terminated array of char. So for this string, hello, with a new line, this is represented in memory as an array of 7 char, H-E-L-L-O, new line, null. And null, remember, is the character whose value is 0. And we saw that we could use this while loop saying while the character that S is pointing to isn't null, display the character S is pointing to, and then increment S to point to the next character. But the thing is that string literals stored in static data are constant, and so actually if you typed in this code and attempted to compile it, you would have either gotten an error or more likely a warning message from your compiler that what you're doing here is not quite correct. Because here I'm passing the address of the little h in hello. That's being received into this pointer S. S is a pointer to a char. But there's nothing in this type declaration of S that implies I can't change star S, the thing that S points to. Let me demonstrate. We'll take a look at my Ubuntu window. So here is the code. Let's see, the name is string literal. So here's the code, and when I compile this, I get, okay, in the GNU C++ compiler in Ubuntu, I get a warning that ISO C++, that is standard C++, forbids converting a string constant into a pointer to char. And in this case, the compiler is just giving me a warning. It's letting me get away with it. A more strict compiler would treat this as an error and just flatly refuse to compile the program. But let's see what the problem is here and how we fix it. To fix this code, what we need to do is to add a const keyword in the description of our pointer parameter S in display stir. So here is the only change that we need to make in order to solve this warning or error message that we're getting when we compile. What that keyword says, and here notice that I'm reading this from right to left. This is a habit that you should get yourself into. This says that S is a pointer to a char constant. if you attempted to write a line of code such as star s gets capital X, let's say, then that would violate this declaration, because this declaration says that s is pointing to a character which is constant. And if you therefore try to change the character by assigning a value to star s, you get an error message. In this case, the value coming in is actually the address of the little h, which is a constant. We can't assign a value to that little h in that static data area where the string literal is stored. And so the effect of const in this case is to simply eliminate the warning message. Let me make that repair in my actual code. All right, so all we're going to do in here is add the word const, so that now when I provide the string literal as the argument to display_stir, and therefore the address of the little h in hello is what's passed in, that's received as a pointer to a char constant, which is what it is. I mean, it is the address of a character which is constant. It is the address of a character that we are not allowed to assign a value to. All right, so with that one little change, if I recompile, now the error goes away, and the code works fine. Okay, so you will often see this keyword const in library function definitions that are manipulating strings to indicate that these functions will not change the strings through those particular pointer parameters. Here on slide 9, we have a different example. This time, we've declared an array of chars, cstir, within main. So this is a local automatic array, and it lives on the stack rather than in static data. And I'm initializing this array of chars with 7 character values. Okay, HELLO, new line, null. So in effect, cstir contains exactly the same string as the string literal hello in double quotes contains. It is a C-style string because I was careful to explicitly put that null character on the end. If I had forgotten that null character, then I would not be able to treat this array of char as a C string. Okay, so when I call display_stir with cstir, the name of an array is the address of the initial character in the array, well, the initial element, in this case, that is a char. And consequently, when I get that address up here, I can loop through the items in the string, or the elements in the string, and display them one by one. Const here is fine, because const is really just promising that display_stir will not change the string. Const does not mean, in that case, that it can only handle string literals as parameters. It can also handle variable strings, such as what cstir contains, as well. It's just promising that it will not change anything about the argument that it receives. So that works fine. This is called array string. Let me just demonstrate that quickly. All right, so here's array string, and if I compile this guy, and run it, it does display the contents of this local automatic char array variable as a string. Okay, now going on to slide 10, we have seen that when you ask for the address of something like an int or a double, what you will get displayed by cout is typically a hexadecimal address of that object. All right, so I here is an int that is initialized with the value 3. X is an array of doubles initialized to contain 3 elements, 2.2, 4.4, 43.21. And therefore, x itself is the address of the double that contains this value 2.2. And when I display these, I'm going to get some kind of hexadecimal output displayed. The particular values I have here are just for illustration purposes. Now, on the other hand, if we use a pointer to character in our cout statement, then the cout object assumes that that char pointer is pointing to the first character in a C string. And so what cout does, instead of just displaying one character, is to continue displaying characters and sequential addresses until we hit the null character at the end of the string. All right, so up here, I have this array A of chars declared, initialized with the 4 char values, capital B, little o, little b, and the null character, so that when I pass to cout the value A, that is the address of the capital B, what's going to be displayed is capital B, little o, b, that is the sequential characters in that C string. The null character is not displayed. The null character tells the cout put to method where to stop. If you create a single char variable, here C is a char initialized with little z, and you pass the address of that single character to cout, then since ampersand C is the address of a char, that is, it is a pointer to a char, cout is going to assume that the little z is simply the first character in a C string. So the little z will be displayed, but then other characters will be displayed up to but not including the first null character that you accidentally encounter. All right, so if we pass little a to cout, as we've seen, that prints Bob, capital B, little o, b, up to but not including the null at the end of that C string. And if we pass the address of z, we might get all this mess displayed until we accidentally bump into a null character following this 9 somewhere in memory after the little z. So how could we display just the actual addresses of the capital B and A and of the little z that C contains? Well, here is the trick on slide 12. What we do is to use what's called a typecast. And a typecast, or type conversion, or type coercion, forces a particular data type to be changed to a different data type. In our case, we can take the pointer to char that we have and convert that to some different kind of pointer, because we know that pointer to char is a special case that cout displays as a C string. Other kinds of pointers, like pointer to int, pointer to double, and in this illustration, pointer to void, are simply displayed as addresses in hexadecimal notation typically. Okay, so to create a typecast, what we do is put a type declaration inside of a pair of parentheses and apply that typecast as a unary operator in front of the object whose data type we want to change. All right, so the type of A here is the address of the first element of an array of char, that is, it's a pointer to char, but we are coercing that to be treated as a pointer to void. Similarly, the address of C is the location where the little z resides in memory, but we're forcing that pointer to char to be treated as a pointer to void. And we may get output that looks like this. Okay, so this is both an example of a particular trick enabling you to display the addresses of characters as addresses. It's also our first example of a general kind of facility called typecasting. And we'll see that C++ provides other ways of doing typecasting as well. On slide 13, we're going to mention a facility or a feature of assignment that we haven't seen before. We know what assignment does. Here we've got a variable I, which is an int, initialized to 3, and using the assignment there, we're saying I gets 4. So that's changing the value stored in that variable I. But it turns out that the assignment operation actually produces a value, which is the value of the object that you've just assigned to. So not only does I gets 4 store the value 4 into the variable I, but the result, the value of that assignment, is 4, the value that was just assigned into the variable I. We can sequence a bunch of assignments, and assignments, unlike all the other binary operators that we've talked about so far, associates from right to left rather than from left to right. Okay, so if we look at the code on the bottom part of slide 13, we're declaring a bool variable b initialized to false, and then we're declaring a char variable c initialized to the null character. Remember that C++ is free format, so it's perfectly fine to have these two declaration statements on the same line of code. Following that, we have a third initialized declaration. I is an int initialized with 0, and then a fourth. X is a double initialized with 0.0. So we have a bool, a char, an int, and a double, and we have initialized each of them with the type appropriate notation for false or 0. The next statement down here says B gets C gets I gets X gets 65.789. Well, actually, if we put in the parentheses that are implied by the right to left associativity, what we get looks like so, all right? So actually, the order in which this is evaluated is X gets 65.789 first, then I gets the result of that assignment, C gets the result of the assignment to I, and B gets the result of the assignment to C. So let's figure this out. X is a double, and so X gets 65.789. Assigning a double value to a double variable works fine. The value of this assignment is the value of X, which is 65.789. That value then gets assigned into I. Now, I is an int. If we assign the value 65.789 to an int, the fraction gets chopped off, and so I gets the value 65. Now that the value of I is 65, we can take the value of I and assign that into the variable C. C is a char. If we were to look at the ASCII character table, we would discover that the ASCII character whose decimal value is 65 is capital A, and that's fine. So C gets a capital A in effect. Capital A, in turn, when that's assigned to a Boolean B, well, remember that 0 assigned to B would set B to false, but anything other than 0 assigned to B makes B true. So the upshot is, as this is evaluated from right to left, first, X gets 65.789. After that, I gets 65, chopping off the fraction. After that, C gets a capital A, assuming we're on an ASCII machine, which we are. And finally, that non-zero value of capital A gets assigned to B, which makes B true. All right, so we don't usually use this implicit type conversion trickery in assignment, but it is common for assignments to be done to set multiple variables to the same value, or for assignment to be done in something like an if test or the test expression of a for loop, so that we can evaluate whether the value that was assigned is true or false, that is non-zero or zero. Let's take a look at an example on slide 14. Here we're looking at yet another string manipulation function. This function is called copy stir. And it's similar to display stir, but with a more complicated interface and somewhat more complicated implementation. First of all, copy stir is taking two parameters. One is called DST, the other is called SRC. And these are for source and destination. Now, the source string is going to be copied into the destination. The source string we're treating as a const. So we're promising in this copy stir function not to change the source string that's coming in as the second argument. But we are going to change the destination. That's the whole point of copying the string. We're going to copy from the source into the destination. And so the destination cannot be declared as a pointer to char const, or if we attempted to change the destination, that would be an error. Finally, notice that copy stir is returning a pointer to char when it's all done. In particular, it's going to return the address of the destination array so that we could have nested copy stir calls if we wanted to. We're not doing that in this particular simple example. All right, so to the copy stir function, we're passing in a destination array of chars. And of course, an array, what we actually get for the array is the address of the initial char in the array. So we're passing in a destination array. We're passing in a source string, which we promised not to change, C string, I should be specific. That is a null terminated array of chars. That could be a string literal, or it could be an array of characters that has a null character stuck on the end. And we're copying the source into the destination and then returning the destination when we're done. Down here in main, I have an array, cstir, of 10 chars. That array is not initialized to anything, so at this moment it just contains 10 garbage character values. But I'm using cstir as the first argument in my copy stir call. All right, so I'm using cstir as the destination array into which this source string, C string, is going to be copied. All right, so the source C string is a string literal, HELLO, and a null. The destination character array is named cstir. Currently, cstir contains garbage, but following the copy stir call, these 6 characters, HELLO and null, will have been copied into the first 6 positions, the first 6 character positions, elements of cstir. We're going to return cstir, which means that we can take the value that copy stir returns and immediately pass that as a value to cout. All right, so when we call copy stir, that's going to copy the C string hello, the string literal hello, into the array cstir, and the return value, which is cstir, is then going to be displayed. So we're going to end up getting hello displayed on our screen. Whew. All right, so how is all this going to work? Well, let's take a look at a diagram of this thing. Here on slide 15 is a diagram of what's going on in memory when we run this program. When we first run the program, the string literal hello gets allocated in the static data area and initialized with the 6 char values, little h, little e, little l, little l, little o, and null. Now, rightfully, I ought to have single quotes around all these. I just didn't really have space in that font to put the single quotes. Okay, so that's a fixed size array of 6 char values with a null character on the end. Once that string literal has been established in static data, then the main function gets called, and in the main function CStir has been declared. CStir is an array of 10 characters. It's initialized with nothing, so it just contains a bunch of garbage values. And it is on the stack, particularly in the stack frame or the activation record for the main function. Okay, so static data gets initialized first, main gets called, its stack frame gets set up, and its local variable CStir gets created. Then copystir is called. When copystir is called, let's see, what are we passing in? Well, the first argument is CStir. That is the address of CStir sub 0. That is the address of this first char within CStir. Okay, that's coming in as the first argument, which is the destination. So the destination is going to be the address of the first element of CStir. And then the source, in the place where the string literal was written, what I'm going to get is the address of the little h. So the address of the little h is coming in as the source parameter value. All right, so that's what happens first, is that copystir gets called, its parameter variables and its local variable get created in the stack frame for copystir. The parameters are immediately initialized, and so what we have now is this situation. The dest pointer points to the first char in CStir. The source pointer points to the first char in hello. Hello, of course, is a string literal. It's in the static data area and it's constant, but we don't plan to change the source argument anyway. We've declared the source as a pointer to a character which is constant, so everything is consistent and there's no complaints from the compiler when we compile and execute this code. All right, now we start executing the statements within the body of copystir. The ret variable is a pointer to char, and it's initialized with a copy of the destination. Destination is a pointer to char, so we're initializing ret with a copy of a value of the same kind. That is, ret points to the same char that dest points to. And there we are. Now we get into this while loop. And the while loop is doing all the work of copying from the source C string into the destination array of char up to and including the null character. Let's see how that works. It's really quite compact notation, so let's see if we can figure this out. First of all, we have some increments in here, and the first question we should ask ourselves is, what kind of increments are these? Well, these are post increments rather than pre-increments. So with post increments, we can just pretend they're not there and worry about them later. All right, so if we ignore these increments, then what we have in the test expression for this while loop is star dest gets star source. All right, so we're assigning the value of star source to star dest. We're doing that in the test expression for the while loop, but that's fine because assignment does have a value. So in effect, what we're saying is, let's take the value of star source and assign that into star dest, and then test to see whether that is not 0. Because if it's not 0, we're going to stay in the while loop and jump in and execute the body of the while loop. On the other hand, if the assignment was an assignment of 0, or null, or false, or what have you, then the test fails and we'll drop out of the while loop. All right, so let's see where we are right now. We're saying star dest gets star source. Star source is little h in hello. We're assigning that to star dest, which is the first character position in CStir. So we do that assignment. Now we test, okay, what is the value of star dest now that we've accomplished the assignment? Is that thing 0 or not 0? Well, little h is not the null character. therefore it's not 0, therefore it's true. So we've done the assignment of star source into star dest, and we've discovered, okay, that assignment was true, so let's do the body. Okay, well, the body here is about as simple as can be. It's an empty body. You do have to have either a semicolon here or an empty pair of open and closed curly braces so that the while loop does have a body of some kind. The most common thing is to just use a semicolon. That's called a null statement, and it does make the overall syntax of the while loop correct. All right, so from the top, we assign star source into star dest. We test whether that was non-zero, which it is, and so we go into the body. Now, along the way here, by the way, just after we test that that assignment was true, and just before we get to the body, we are now going to do our post increments on the source and destination pointers. Okay, so here's what's going to happen as a result of those post increments. The source is no longer pointing at the little h, it's pointing one care further along in memory, so it's pointing at the little e in hello. The dest is pointing one care further along in the destination array. Okay, so we copied star source into star dest. We discovered that that was true. We post incremented dest and source, so those pointers are now pointing at the next items. And we do the body of the while loop, which is empty, and we come back to the test expression again. All right, so we're back in the test expression in the while loop. We assign star source to star dest. Okay, so the E gets assigned to star dest, like so. Well, E is not the null character, so we're going to increment the two pointers. Source now points at the first little L. Dest now points at the third element in C-stir, the sub2 element. And we come in here and do the empty body. After we've done the empty body, we come back up to the test expression again. And here we are. Now this is going to keep rolling along. The little L is going to be copied from source into dest, and the pointers will be incremented. And of course that will still be true. And then the next L will be copied, and the O will be copied. And after those are copied, we will be in this situation. Okay? The source pointer will be pointing at the null character at the end of the string literal hello in static data. And the dest pointer will be pointing at the sixth, the sub5 character in C-stir. Notice, by the way, that after we initialized ret to point to the first character in C-stir, the sub0 character in C-stir, we never changed ret again, so ret is still left behind pointing to the H in the copy of hello. Now, when we evaluate our test expression, star source, which is the null character, is assigned to star dest. So star dest gets the null character. The null character is the character whose value is 0, and 0 is equivalent to false. So now the test fails, and we drop down to the return statement below the while loop, and what is it we're returning? Well, we're returning ret. We're returning the address of the little h. So what comes back from copy_stir is the address of C-stir sub0, the address of the little h in the copy of hello, and so hello is going to be displayed on the screen. Let us demonstrate that that actually happens. We'll flip back to Ubuntu. This is copy_stir. There we are. Okay, so we So here's our copy stir function. We're copying from the source to the destination, and we're returning a copy of the destination when we're all done to the point where copy stir was called. Let's compile and run this thing. And if it works, I should have hello, that is a copy of the C-stir array, displayed on my screen. Yay, it works. Okay. So what we've done here on slide 14 is another so-called idiom in the C and C++ languages. It's a piece of code that you're expected to be able to glance at and immediately know what it's doing. This magical while loop copies a source C string into a destination char array up to and including the null character. And the destination is returned when the function is done doing that job. In fact, in the standard C++ library, the name of this actual function is strcpy rather than copy stir. It's strcpy, and it has the same parameters in the same order and the same return value as what I've demonstrated here with the copy stir function. All right, well, next up we're going to take a look at the switch decision, which is an alternative to if-else chains. It's very useful if you're doing a comparison of some expression value against a specific list of discrete integer values. Now, integer here doesn't just mean int. It means bool or char or int or long. Any of the integer data types can be used in the switch. Let's take a look at a specific example. Okay, so here I have a function on slide 17 called WhatIsIt. And the WhatIsIt function takes a single char parameter c. This whole business here is the switch, from where it says switch c with the opening curly brace all the way down to the matching closing curly brace. And within there, I'm going to erase all this yellow. Within there, what we have is a sequence of what are called case labels, which are like targets to jump to from the top of the switch. So let's suppose that the value that gets passed in is the character 7. Okay, so we're going to switch on the character 7. And we do that by looking at all of the so-called case labels. Now, character 7 does not match character 0, so we skip that case. Doesn't match character 2, doesn't match character 4, 6, or 8. Doesn't match character 1, 3, 5, or it does match character 7. We have found our matching case label. And so having found our matching case label, what we now do is to look for the next available executable statement, which is this cout statement. And so the message is going to be displayed that 7 is odd. The way we get out of a switch is in one of two ways. Either we just fall off the curly brace at the bottom of the switch, or if we're in the middle of a switch somewhere, it's more common to have what's called a break statement. And the break statement immediately jumps out past the closing curly brace at the bottom of the switch. So, in other words, a case label specifies where to start executing statements. A break statement, on the other hand, specifies where to stop executing statements and break out of the switch to whatever follows the switch. If there is no break, then control falls through to the next statements. Let's see what's going on there. Let's suppose I call WhatIsIt, and the character that comes in here is character 0. All right, so I say switch on character 0. Well, here's our match. Case 0 is a match, and so that tells us where to start executing code. We therefore execute this statement that displays 0 is 0, that is the character 0 is 0. Notice that there's no break following that statement though. So we fall through, these cases are not executable. They're sort of like signposts saying where to start doing something, but they themselves don't do anything. We fall through and we execute this next statement that 0 is even. Okay, well that's correct. 0 is even, so that's fine. Then we hit a break statement, and that drops us out past the bottom of the switch. So this so-called fall-through behavior is sometimes used intentionally. And in this case, if we're asked, what is it, and the parameter is the character 0, the behavior is what we want. We match case 0, we execute that 0 is 0, we fall through and execute that 0 is even, we then continue and find this break, and the break drops us out of the switch. Now, each one of these case labels is only permitted to occur one time within the switch. So I have case character 0, character 2, 4, 6, 8, 1, 3, 5, 7, 9. If I had case 9 appearing twice, then the compiler would yell at me, I'd get an error. It is also optional but common to have a default label in case none of the individual cases match. So let's suppose we called WhatIsIt, and the character argument that came in was capital A, let's say. Okay, well capital A is not 0, it's not 2, 4, 6, or 8, it's not 1, 3, 5, 7, or 9. We've exhausted all of the cases, so we match, in this case, the default and display that A, capital A, is not a digit. You're only allowed to have at most one default. However, it doesn't matter whether the default is at the bottom or at the top or in the middle somewhere. Most people put the default at the bottom, but you don't need to put it there. And in fact, it is possible to have a switch that does not have a default. In that case, if none of the individual case labels match, then nothing is executed. No statement is executed within the switch. Here's a test run of WhatIsIt. If we call WhatIsIt with character 5, okay, character 5 goes into the switch and it matches this case label. So the output is 5 is odd, okay? 5 is odd is our output. And then we hit the break and drop out of the switch. And after we've dropped out of the switch, we also are done with the function, and so the WhatIsIt function returns. In this next call, we're saying WhatIsIt capital A, and we already did that as a demo. So capital A comes in here. It matches none of the labeled cases, so it comes down here to the default, and we display that capital A is not a digit. All right. We also did the case of character 0. Character 0 is 0 and is even, and then we break out of the switch and return from the function. For the character 4 is going to match this case here, and we'll display 4 is even and break out of the switch and return from the function. All right, so we just get one line of output from 4 is even. Now this final one is sort of interesting. It's intended to be an amusing trick and illustration. We're saying, WhatIsIt 9? Notice that I don't have 9 in quotes there. So what I'm actually passing is the integer value 9 down to WhatIsIt as a char. What in the world does that mean? Well, remember that these character constants like quote 5 quote and quote capital A quote are really just representations of bit patterns. And if we look up in the ASCII character set, we can see that capital A is given the bit pattern corresponding to the bit pattern for the decimal value 65. Likewise, character 0, quote, turns out to be the same bit pattern as the decimal value 48. All right, well, 9 is a decimal value, and if we look up in the ASCII character set, what is the character that has the bit pattern corresponding to decimal 9? It turns out to be the horizontal tab. So when we pass horizontal tab into this function, well, horizontal tab obviously does not match any of the labeled cases, so we drop down to the default and we display horizontal tab is not a digit. That's why in the output we have all of this space here, okay, because there are 8 characters of space before we get to space is not a digit. Notice that there is a space here in the space is not a digit output. Let me prove that we get what I claim. Let me flip back to Ubuntu. Here is the program. And by the way, this way that we've written the code on slide 17 will work, but it's very unusual formatting. I formatted it this way to force it to fit neatly on the slide, but usually the way people write switches is to line up the cases vertically instead of laying them out horizontally. So on slide 20, this is more conventionally how you would see the switch written. And so that's the way that I've written it in the actual program, WhatIsIt.cpp. If you compare the order of the tokens, you'll see that the order of the tokens on slide 20 is the same as the order of the tokens on slide 17, so far as the switch goes. Okay. All right, so there's the WhatIsIt function containing the switch. Notice the comment here, the loud capitalized comment here that's very often used if you want to indicate that there's not a break there and that that's intentional. Here's the main function that exercises WhatIsIt. And when I compile this thing, and run it, okay, you see that I get what I claimed. There's actually a tab character here, followed by space is space not a digit. Okay, so there's a horizontal tab being displayed right there. Okay, let me back up to slide 19, which I skipped over. I think I said some of these things aloud, but let me be careful. You're not allowed to have duplicate case labels. You're only allowed to have at most one default. Generally, people put the default at the bottom, but it could be at the top or in the middle somewhere. And these case labels have to be integers. They can't be floating point numbers. They can't be pointers. They can only be integer constants, and that includes things like the word true, the word false, int constants like 5, 9, 47, char constants like quote 0 quote capital A quote, and so on. But no pointers, no floating point numbers, no string literals, no arrays, just integer constants. Okay, so that gets us to the conclusion of Lecture 9, which was not quite so brief as I anticipated, but nevertheless important stuff. There we go. Okay.